Welcome to the part 3 to the practical organic chemistry. I wish I can have enough time for going over all of the fundamental physics with you, but unfortunately I have to move on. So here I have some fragmented concepts in this video. This might help you to understand each spectroscopy and spectrometry better, and connecting the structural feature of the organic compound as matter with the spectroscopy concept, where the photon has to interact with that. So when you deal with the object that consists of two or multi-body, you hear sometimes center of mass or reduced mass. So the center of the mass, I'll explain with the two body system. By just looking at it, you have a lighter and heavier object connected. So probably the center of the mass is not in the middle of the bonding, but more toward the heavier one. So to mathematically to find the exact location of it, you have distance x1, x2 from certain imaginary point, and then you put this as a center of the mass, distance from the same origin. Then this is the mathematical formula, and here the x is not actually the distance of center of the mass, but it is the bond length here. So if you want to stretch or compress, you need this much of force, and that's proportional to this force constant. And you'll see many in physics and the chemistry, many symbols look alike, and you need to clarify them when you use. And also from books to other books, or professors to other professors, they use different symbols. So yeah, you need to clarify what each symbol exactly meaning. So later in other formula you may see K, but it may not necessarily mean it is force constant or the distance between two objects and so on. But anyway, so that's center of the mass. But reduced mass can be derived this way. Reduced mass symbol is mu. So when you think of the two-body, multi-body situation, kinetic energy of the whole molecule is the sum of the kinetic energy of individual object in the whole. Then you know the formula, but when the body is moving along, you can say their speed, in this case velocity, be represent not volt but velocity. When they are equals, you can put this in this form by making m sub 1 squared. Then you can take it out this way, having the p squared divided by m, and then you can make it out this way, and then you convert it that way, and this term here is 1 over mu, and that is reduced mass. So in a certain mathematical manipulation of equations with a multiple body object, you need to combine all of those individual mass in one term as a reduced mass. We'll see this in the IR equation. Then when you look at this corner, say you have a spinning object like an electron, and you have a couple terms to understand. So you kind of have three sets of velocity and acceleration. You can first think of the angle change in a given time. So you will have angular velocity, and you can think of the tangent speed. So depends on how much angle it moves, the tangent speed also changes accordingly. But angular speed, the amount of the degree angle you change per time, is not necessarily same as the tangent distance per time. So those are related, but they're not same. Also, the object is not traveling linear. It is making a circle, so the speed on the arc is different from the speed, velocity of the angle or tangent velocity. So the velocity on the arc, they're different as well. So like I put the elements of this vector on the x and the y direction. Using those parts, you can write it out this way, and then you can find each quantity using sine and cosine, and you can express it this way. So if you derivatize this tangent speed in terms of the time, I skipped it, but if you derivatize them, you will end up getting this. So velocity square over r will be equals to the acceleration. Then using the definition of the radian, not angle, like this, you know, when angle moves certain amount, the radius length equals to the arc. That is the degree put as 1 radian. If you go by that definition, you can get these equations. So only because you use radian, the angle you travel multiplied by distance will be the size of the arc. And then the angular speed, if you multiply it by the distance, you get the tangent speed. So the longer, the bigger the r is, with the same angular speed, you get much greater tangent speed. That also goes same for acceleration. The angular acceleration, if you multiply r, then you get the tangent acceleration. And this is the relationship between velocity, tangent velocity, or the angular velocity to the radian acceleration. And these come in handy later on. Thus you can also deduce these equations out of them, and therefore you can make up these formulas. So this is a time, but it's the time it takes to make a full turn. Out of 2 pi whole turn, you divide by the velocity in angle, right? So this is the distance of the angle that equals to velocity times time. But when you make one full repeat, the amount of time is going to give you whole circle, so 2 pi. Then also using the equation over here, here you can make up this equation as well for the period. Then when you have a spinning object, not circle around, but self-recession, then you can describe the certain property out of the rotation. You can have a two different rotation. According to the rotation direction, physicists created of making the vector direction with the intensity. So using Fleming's right hand rule, with this rotation you put it as a positive rotation, then the angular momentum is expressed going up. Depends on the speed, the angular momentum could get greater, and the opposite direction could be then negative rotation, and then angular momentum will go downwards. And that is the way physicists and chemists describe spin. So nuclear spin or electron spin. So when you see the arrows up and down, you know that's the angular momentum came from the actual motion that's rotating counter or clockwise. Again, my intention is not to explain all of the fundamentals of these physics, but giving you like chance to review and remind of yourself. We are dealing with the vectors, so you need to know how to add them and multiply them. So when you have a vector A and the B, you know you can basically put them in the Cartesian coordinate. So 4, 2, 3, 1, right? And then 1, 2, 1, minus 1, minus 2. So when you add them up, you can use geometry, make up a parallel lines and come up with a addition of the two vectors. Then you can measure out how much it is, but we certainly can also use this complex number way of expressing vector. So you multiply, and then I times I is -1, but ix the same thing, right? Ix and ix -1, but the opposite one becomes 0. But you don't multiply here, you just add them up. So you just add them up, and these two get cancelled, and you get 8 i's of x. So this probably is y component 0, x component 8. So that's the intensity and the direction of the vector in this addition. For the multiplication of two vectors, you can come up with a scalar easily by doing this. But also, you can put it in this way for the three-dimensional case. This is for the two-dimensional case in general. Then you will come up with this kind of outcome, and that is corresponding to this matrix. So in the space, because you have to apply to the a physical model, when you multiply these two A and the B vectors, depends on which one you multiply to which one, you may come up with a vector that's going upward or downward. Just like the previous spin motion angular momentum type of description. So this will come in handy later when you discuss NMR in theory in depth. Okay, now let's look at the harmonic motions with the cosine function briefly. Here I have vibrating IR kind of situation. There we have electron spinning around orbital. So the xm is increasing in positive, then increasing in negative in this manner according to the time progression. When it makes full circle, full turn, you measure the time, and that will be your period. Or this case, when it starts from there and it comes back on, it's same as from the top, it goes way down and then come back up. In terms of the vector, when you go down, it is going downward, and then when you come up, it is going upward. So when you moved x degree, this much degree, you can get the x of y component this way. So with the angular speed, given time, you travel this much, then this x of m became x, and you expressed it this way, and the angle is obviously substituted that, and that makes sense. Then after turning whatever times, repeating the period whatever times, it's going to be anyway same number. Then traveling this much more time will determine what size of the x you get, because this is anyway bring the electron back the starting. Then you take the derivative of this formula by t time, then you get this. If you do one more derivatization, then you get the acceleration, and it becomes like this. Then we can convert this to this, something we saw before. Yeah, using the relationship of the velocity, tangent velocity is equals to the angular velocity times distance. Previously we used the distance r, but now it's x. Like I said, symbol changes, depends on how you set up. So let's go by the concept. Then overall, the total energy also can be expressed using sine cosine function. So there you have potential energy plus kinetic energy makes up the total energy. Then you know these equations. For the kinetic, the potential, the axis distance between the two parties, and the k in this case is a force constant, like in the spring. In the previous slide I showed you that the k as a force constant. Then you put these values as a function here and there, then you get this. Then you realize that if you take these units out, you get these, and you know this is equals to 1, so you get this as a total energy. So in this expression of the total energy, the k is actually a force constant. Also, you come over here, you can see if you exerted force to make this object turning at a certain acceleration, you can come up with this equation using the acceleration equals to that. So you come up with this, then you arrange them this way, then you can put it as F equals kx. And remember the k as a force constant. Now you know what consists of the force constant in the rotational motion. And of course, oscillation motion as well. This applies to the harmonic motions in general. Then from there, you can rearrange them this way to come up with the elements that makes up the angular speed, angular velocity basically. Then I showed you before, even over here, the period equals to this. So 360 degree divided by the angular velocity will give you the period, the time. Then this angular velocity formula is here, and you plug it in, and that's your period. Using the period, you can calculate the frequency. So how frequently that is rotating or that is vibrating. So for IR and the UV, even for NMR. Some books says the frequency using F as a symbol or nu as a symbol. But what I mean here is the frequency. So if you take the inverse of this, you get the frequency formula. So if you go back to the our model, in order to have the light interact with the matter, you need to have the matter, right? The object motion that should be matching with the frequency of light. So the frequency of light must be equal or similar to that of the object to get absorbed. In other words, for having resonance. So this is the formula that we derive out of the Planck's equation, and now it had the elements, the constants, or the measurables of the object. This is how we know that depends on if we know, right, what frequency of light we used and that is absorbed well. If you know by comparing the two light sources that's measured by the machine, then we can get the idea of, say, mass and the force constant. So how heavy those balls are, meaning what atoms you have. If you have a multi body in the molecule, then this has to be reduced the mass. Also, we can measure whether the bond is a single bond, double bond, triple bond, or stronger single bond than the other single bond. We can actually measure out. This will be my last slide before we actually get into the spectrum. This is a situation where you have nuclei with an electron, and they are in the electromagnetic field. Because the nuclei creates electric field, and the electron itself is also creating electric field, and nuclei is spinning, electrons are spinning, and also electron is moving around, and thus they are creating magnetic field. So as this nuclei spin, it creates angular momentum. Electron creates its own angular momentum of the electron spin. Also, because they are creating magnetic field, they have a magnetic momentum. So the magnetic momentum is defined this way. This is one of the ways. If you apply external magnetic field, how much torque you create, how much force for them to turn you create, that is the magnetic momentum. And torque in physics also is defined this way, right? The change of the angular momentum over change of the time. And these are the ways of manipulating torques, especially for the rotational object. And one other way of defining magnetic momentum is this. The ratio of magnetic momentum in the same motion with this much of angular momentum. The difference is both are created by same body. The only difference is this physical amount has magnetic property in it, so the ratio is given in the gamma. And we call it gyromagnetic ratio. So it's basically telling how much magnetic properties is created and is there in making rotational motion. And also, if you can measure magnetization of a certain object or certain area, if you divide, if you multiply that by the volume, then that's how much magnetic momentum you have in that area. So in order to calculate the magnetic momentum for the electron that's moving around on the certain orbit, then you have to multiply the current by the area. Then you know the current is amount of the charge in a given time, especially the period when it makes full circle. Then the period, we talked about it before, so you plug it in and you get this. Now you have a relationship with the amount of charge and the angular momentum. So you have a more, angular velocity. So if you have a more angular velocity, you get more current, then you get more magnetic momentum. So if you plug that in here, where the I is in the definition of the angular momentum, then you go here and you can drive, right? Like this. Then you know this is angular momentum. So you replace this with the angular momentum, and now you have the relationship between magnetic momentum and angular momentum, and the ratio supposed to be gyromagnetic ratio, and that's this quantities right there. So this means, if you look at over here, if you have, for example, a nuclei you are trying to detect with NMR, the more charge you have, you get more gyromagnetic ratio, which we will deduce later. But if you have a more of that, then you get the more energy difference for one energy level to the other energy level. If your nuclei is heavier, then the ratio becomes smaller, so you get the energy gaps smaller. Okay, so this was one of the definition for torque. Torque is like energy, right? How much energy? So the equation here, you find it there. So how much torque, how much energy you give to the system to make it transition to the excited state. That's what it means if you kind of combine the concept with the physical model and the quantum model. Also, we know the definition of Lamour frequency for the gyroscopic ratio. You can convert frequency this way, then you plug it in here and you can derive the equation that you need to remember for NMR. So the more gyromagnetic ratio, you get more energy split for the ground spinning and excited level of spinning, and you get the more magnetic field applied, the energy gap also increases. So that's external condition that we apply to the system, and this gyromagnetic ratio is the object, the sample intrinsic property, and as you can see has to do with the charge, amount of the charge and the mass. So we have to take it to the NMR, because when we put the sample in the NMR machine, we are applying magnetic field. Without applying it, whether the spins go right way or left way, that's causing the momentum going up or down. The energy level for these are same. Whether you put this as alpha or beta, that depends, but the energy level is the same. It's the same amount of scalar For alpha and beta, it's just the directions opposite. But when you apply magnetic field, then these magnetic momentum, basically, they face different situation. So if this was an S, and if this was a S, for example, they feel different. Therefore, the energy splits. So each spin, they're not same energy anymore, so they prefer one direction. Depends on what type of a magnetic field or how much magnetic field you apply. So when you apply more magnetic field, the energy gap for these two spin increases. With a small amount of the magnetic field, that the energy gap of the two is small. When this is weak, the interactions weak, so the difference is smaller. If you apply very strong magnetic field, the interaction between the external magnet and internal magnet of the quantum particles changes. That's when you deal with the same particle, right? When you deal with the different atoms, then this gyromagnetic ratio part changes, and that also changes the energy gap. That's when you have a hydrogen NMR, carbon-13 NMR having different scale of x-axis that's relevant to the energy. So X is most of time for spectroscopy, the quantity is related to the energy. Y normally has to do with absorptivity, the absorption. Then using this equation, you can calculate the population. What it means is basically the more energy gap you have here, you get a lot more the alpha, more stable state than the B. If the energy gap decreases by applying less magnetic field, or you have a smaller, not smaller, but a small gyromagnetic ratio atom, if you look into it, that's the atom that has more charge and the light. Then you get more population going to the beta. So alpha and beta, the population of the nuclei, the difference is a lot small, and it's almost degenerated. So if we go back to the main principle of spectroscopy, say you created energy gap with the applied magnetic field. Without this, you cannot measure NMR signal. So with the applied magnetic field, you have lower energy and higher energy, the quantum state. Not any arbitrarily number of energy is going to work. It has to be only this going to that. So if you give photon to overcome this much of an energy gap, again, it doesn't mean it's very massive or mass related energy. It is the frequency of the photon that matches with the frequency. In this case, this. So if you give not enough energy light, meaning not enough of the frequency, the alpha spin, whichever the spinning was trying to flip to this, meaning trying to spin other direction, that wouldn't happen. If you give equal or little more frequency energy, light works. Obviously, if you give exact same frequency, it works the best. If you give a little more, it works less, because the interference of the two waves, they're not perfect if you are not matching perfectly, so the resonance may not occur readily. So this video, especially among all three lately, is really boring video. This is why I don't like giving out summary or review. If you try to explain from the bottom, you know, build up one at a time like I do with organic, it's much more fun. And if you like to discuss this personally, you can always contact me. And I hope I can put up more video, taking more time going over the physical concept of the molecules. But for now, this should be enough to start spectroscopy. So I'll see you with a more chemistry next time. So good night.